Section 1.2 is called Gaussian elimination and Gauss-Jordan elimination. Both of those are techniques we can use to solve a system of linear equations by representing them as matrices and then manipulating the matrix. So first up, let's define matrix. A matrix is really just a rectangular array of numbers, but we call it an m by n matrix. M by n means that you have m rows and n columns. So for instance, if we had the matrix 1, 2, 3, 4, 5, 6, 7, 8, this has 2 rows and 4 columns. So it's 2 by 4. And it's always row and then column. And typically what we do is we use capital letters for naming matrices. So like this matrix would be, I call it matrix A. And the entries over here, notice they're all lowercase a's. And this is the indices on here tell you the row and the column. So like this right here, A23, that means it's row 2 and column 3. Normally you don't use commas between those unless you get into a really huge matrix where you've got more than more than 10 rows or columns. All right. So what do we use matrices for? There are a lot of things that we can use them for, and we're going to see several things throughout the semester. But for now, we're going to use them to represent systems of linear equations. So if you take a look at this, here's a system of linear equations. And here it is as an augmented matrix. Now, augmented only means that it has this line here. That's called the augment line. And it really corresponds to the equals. Over here, if you look at the coefficients on this equation, 2, 4, and 1, you've got those here, 16. This next row gives you 0, 2, -1, 4, and then 1, 0, 2, 5. So the augmented matrix really kind of represents everything that the system represents, but it does it in a more compact manner. We don't have pluses that don't need to be there. We don't have, I guess we do have zeros in places of blanks, but anyway, it encodes all the stuff about the system. The only thing it doesn't encode is the variable names. So a lot of the time when I'm doing this, just as sort of a mental reminder to myself, I guess it's a written reminder, not a mental one, but I'll label the columns there, so that I know this is the coefficient of y in the 3 different equations over here. So, normally when we solve a system of equations, there are different things we do. You can always multiply an equation by a constant. You can add equations together and stuff. So the elementary row operations, these are all the things that we can do to a matrix, to an augmented matrix, without affecting the solutions to that system. If you look at it, let's see, interchanging 2 rows. If you interchange 2 rows on a matrix, then all that does is it's just like writing the equations in a different order. If you multiply a row by a non-zero constant, that's just like multiplying an equation by a non-zero constant. And adding a multiple of one row into another, we do that all the time with the equations when we're solving them by elimination. So this just kind of codifies those 3 operations. And we say that 2 matrices are row equivalent if you can transform one of them into the other by the elementary row operations. And this fact here, I sort of already gave it away. If you use those row operations on a matrix, it doesn't change the solution set. So we're going to look at putting matrices into nice forms to get the solutions. The first thing I want to talk about here, though, but before we get into those forms, I want to talk about Gaussian elimination with back substitution. And I'm going to put that in the next video.